Good morning and welcome to our lecture today from NASA. We are really glad that you came, and we got sunshine here on a cloudy day. So we'll get rain later. So this is a good day to hear about the sun, which will return, I'm sure. I'm Stephanie Marcus from the Science, Technology, and Business Division. And this is our 13th year. We have a list of lectures for next year, another 8. And so we're ready to go to town. I'd like to introduce, now that I know how to pronounce her name, Nicholeen Viall. She explained how it was French and then it was anglicized, so she's not Viall, as I'd been practicing for the last several weeks. She began her studies in astronomy and physics out in Seattle, Washington, University of Washington. And then she did her graduate work, both her master's and her PhD at Boston University. And she was a NASA fellow and then a permanent NASA person. But she must be very valuable because she got one of the early career awards from NASA last year. What is that called? The Early Career Achievement Medal. Congratulations. And a great honor that surprised her, which was the Karen Harvey Prize from the American Astronomical Society's Solar Physics Division. So she knows her stuff. Right now she's Deputy Project Scientist for the Stereo mission, which is one of the solar missions. And she'll update us on that mission and all the other solar missions. We've heard about the Parker Solar Probe, and the Solar Dynamics Observatory has been out there a long time. Wind spacecraft actually launched in 1994. And the upcoming one, which you might have seen the little handout, is PUNCH, which really is a great acronym. So please help me welcome Nicholeen Viall to the library. Thank you.
All right, thank you everybody. So I'm here to talk about the sun. The sun and the solar wind and the solar corona and the space environment. And you might not know what any of those words mean. Hopefully then the sun you knew, but the rest of the words we're going to talk about, and I'm going to explain what all of those words mean. So this is sort of just a teaser image that I have right here. This is the total solar eclipse from 2008, an image from the total solar eclipse. And so this gives you sort of a sense of how the sun is creating its space environment, the space environment that we live in. That's sort of what we're seeing here, and I'll get more into that in a little bit. All right, but I'm going to start with this video here. This is sort of a more typical view of the sun, sunset. How do we think of the sun on a normal day? Sunset is sort of a way that we normally think of the sun. On the left, this is actually sunset on Mars, but even there it kind of looks typical, right? It's kind of just sunset. This is sunset on the Earth. It's blue at Mars. This one was taken with the Mars Curiosity rover. Maybe I'll play it again here. Yeah. This is taken with the Mars Curiosity rover. It is blue because of the dust in Mars's atmosphere, and so that filters out the red light, and it's the blue light that comes through for sunset on Mars, whereas on Earth, it's the opposite. It's the red light that comes through and the blue light that's scattered. So that is a difference. But still, it kind of looks the same on Mars, kind of similar. The sun looks kind of similar. That's sort of how we're used to seeing the sun. A total solar eclipse is something that happens every once in a while, and this is a different kind of way to look at the sun. This is an atypical view of the sun. Now, first of all, you should never look directly at the sun unprotected. There are special glasses that you can get to protect your eyes from the sun. You should never look directly at it. But during totality, during a total solar eclipse, which is when the moon comes between the Earth and the sun, blocking out the bright disk of the sun, then it is safe to look at what remains. And what remains is the solar corona, the atmosphere of the sun. That's what we're seeing here. This is just in white light, just like what you see with your eye. So the solar corona is much, much less bright than the solar photosphere. That's what we call the visible surface of the sun. That's what you can see here. How many people saw the total solar eclipse in 2017?
A partial total.
So here in DC, it was partial. There was totality went across it started in Oregon and came across the United States and went out through South Carolina. It was pretty amazing. It lasted a little over 2 hours, an hour and a half maybe. I think it was about an hour and a half that it crossed the United States. It was pretty amazing. I was on location in Salem, Oregon, doing NASA coverage of totality. It was an amazing experience. So I highly recommend seeing totality if you can. The partial solar eclipse is pretty cool too. That's where the sun partially comes in front of the sun. The moon partially comes in front of the sun. To see the partial phases, though, you do have to wear the safety glasses. All right, so here's some other images also of the eclipse. What you can see right here is what's sometimes called the diamond ring, which is just after the sun has gone behind the moon and it just starts to peek back out. There's a flash of light. So that's what they're capturing over here. And then over here on the right, I don't know if that's showing up so well with the reflection, but there's, you can see some red around in the solar corona here in the atmosphere. The red is from cooler material. The chromosphere, it's one of the layers of the sun, chromo meaning color. So we call that the chromosphere. I'll show you that a little bit later, but you can get a hint of it during a total solar eclipse. All right, this is actually from the total solar eclipse on the 2017 total solar eclipse. This is just sort of a processed image. So with your naked eye, our eye doesn't quite have the resolution or the dynamic range to see all of this high level of detail. But with some image processing, you can pull those details out. So the first thing I want you to notice is how enormously complex the solar corona is. There's a ton of structure here. There's little structures that seem to all be aligned. There's structures that are curved. It's enormously complex. So this is the sun's atmosphere. What you're seeing actually is density. It's the electron plasma around the sun. That's what you're actually looking at. You're just viewing the plasma around the sun. So when we look at this view of the sun, two questions come to mind, two questions that NASA is investigating. First of all, where did all of this complexity come from? What's making this complexity? What is going on the surface of the sun and below to make all of this complexity? That's the first question. The second question is what happens as this plasma expands out into space, as all of these electrons expand out into space? What happens to that as that fills the solar system? So both of these questions are things that NASA has launched spacecraft to investigate. All right, so there's one thing, well, there's a number of things, but the first thing I want you to remember is that different wavelengths, so different kinds of light, on the solar atmosphere, when we look at the solar atmosphere and different wavelengths of light, we're looking at different temperatures. That means that the plasma, or the plasma is when the electrons are no longer bound to their protons. Different wavelengths correspond to different temperatures. So when we look in different ultraviolet or X-ray light, you're actually seeing different temperatures. And because of the temperature structure of the solar atmosphere, different temperatures means different heights. All right, so keep that in your head, that different filters are different temperatures and different temperatures are different heights. So we can sort of probe the layers of the atmosphere. Whoops, I didn't play the video. All right, here we go. Okay, so this is the old man in the sun, like the man in the moon. Can you spot the face? It's not always there, but the sun happened to configure its complexity to kind of look like a face in the sun. So that's visible light right there. This is another channel, 1600 angstroms. This is hotter now. Now we're getting up to 50,000 Kelvin. Now we're at 600,000 Kelvin. Now we're at 1,000,000 Kelvin. Now we're at 2,000,000 Kelvin. Now we're at 2.5 million. So it just keeps getting hotter and hotter. 6 million Kelvin. 10 million Kelvin. And there's the man. And then this is a special filter that looks at the magnetic field. Kind of looks like a monkey. So what's cool is you kind of get a sense of how, when you look at the different wavelengths, there's different structures. So that complexity that we saw in the total solar eclipse, it comes through in different ways depending on the temperature and therefore the height that you're looking at. So I'll say a little bit more about that. The sun is very bright and it's highly complex in ultraviolet and X-ray light. Now, this is one of the reasons that NASA has to fly spacecraft to look at all of this. It's because the ultraviolet light and the X-ray light doesn't come through to the ground, so we have to be out in space to see it. So here what you're seeing is Solar Dynamics Observatory, all of those different wavelengths that you saw, but we're seeing them in different slices. So you can kind of see the complexity and then watch as the different filters rotate across the complexity. And it looks different in each of those filters. So remember, each of these colors is a different temperature, which is a different height in the atmosphere. So the fact that the atmosphere, the solar corona, emits in this X-ray and ultraviolet light is because it's incredibly hot. In fact, it's hundreds of times hotter than the solar photosphere, the visible surface below. In fact, some areas it's 500 times hotter. So I think you saw there was 1 million or more Kelvin in the corona versus a 6,000 Kelvin photosphere. So that's really crazy that it's hundreds of times hotter in the solar atmosphere. That would be like if you were standing at a fireplace and as you walked away from the fireplace, it all of a sudden got hundreds of times hotter. That's not the way that physics usually happens. But we know that it's ultimately that magnetic field, and I'll show you some more information about that. It's the magnetic field releasing energy up in the corona. That's what's making it so hot. But we're still investigating exactly how that energy takes place, how that energy release takes place. All right, so back to the sort of standard view of the sun, back in the optical light, visible light, like you would see if you were looking at the sun with these special glasses. This is taken with Solar Dynamics Observatory. Solar Dynamics Observatory kind of looks at the sun in high definition. It's like high time resolution, high spatial resolution, higher than we had ever taken of the sun before, but all the time. It's continuous coverage. So we have a lot of information about the sun now. So the first thing you should notice is these dark spots. Those dark spots are sunspots. They're actually, we know now, they're regions of concentrated magnetic field, so concentrated that the light is actually suppressed there. So these sunspots, long before we knew what they were, people have been measuring them. In fact, there's evidence from thousands of years ago of people measuring sunspots on the sun and watching them. All right, here's a video where we, again, go through the layers of the sun. We start in the photosphere, and then here's one of those ultraviolet megakelvin type plasma, million degrees, million Kelvin. This is another layer added on top of that where you can see the next hottest layer, like 2.5, 3. Then here's a model of the magnetic field where they're rooted in those sunspots, and then it comes out into the corona. So we know that the magnetic field is what's causing a lot of that complexity. How the magnetic field is behaving, how it's dynamic, that's what's creating a lot of the complexity, and it's what's creating the heat in the solar corona. So one thing to remember is that the corona, the solar atmosphere, is so hot and so highly ionized that the electrons are stripped away from their atoms, from the protons primarily. And so they're charged particles, it's plasma. And the key takeaway is that, to remember throughout the rest of this talk, is that charged particles or plasma can't cross magnetic field lines. It has to flow along the magnetic fields. So you can kind of see that the plasma is following those magnetic field lines. All right. So NASA looks in the ultraviolet and X-ray. That's what this image is down here of the sun. This image in the middle is the total solar eclipse from the ground. And then this outside field of view, even though it's false colored red, it's actually taken in white light. This is from an artificial eclipse. So the other thing that NASA does is it creates artificial eclipses, artificial total eclipses, so that we can see this solar corona in white light, but all the time. So this one was actually taken with the SOHO mission, but at the same time on the 21st in 2017, so that we could line up the stuff going down lower in the atmosphere with the stuff going on higher up. And you can see that this magnetic field that's creating all of this structure is creating structure that persists all the way out, really far away from the sun. And in fact, the solar corona is so hot and it has so much energy that it continuously streams away from the sun. And it flows outwards to become the solar wind. It's supersonic. It goes incredibly fast, 400, 500 kilometers per second. So what you're seeing here is the solar wind. That's Mercury in our field of view. These are a series of images taken with STEREO, the Solar Terrestrial Relations Observatory. This is, again, white light that you could see with your eye if you had a sensitive enough eye, and if we didn't have scattering through our atmosphere and things like that. So this is one of these artificial solar eclipses that we create from space, where there's the sun, this is further out, and then here's all the way out, and you can see this plasma just continuously expands outwards and fills the solar system. It fills the whole solar system. This is kind of a cartoon representation of what we do at NASA, what NASA heliophysics, that's the big word, heliophysics, that we use to describe this sort of study of the sun and how it impacts the solar system and how it affects Earth, sun-Earth interactions. You may have heard the word space weather, the term space weather. That's also means, what is the sun doing and how does that affect our space environment? So this is just meant to be a cartoon, it's not to scale, it's a cartoon representation. Some of this, though, is from real imagery of the sun. But there's the core where fusion is going on, making all this energy, the convection zone right below the surface of the sun. There's a lot of roiling and boiling going on that stirs up those magnetic fields. That's where a lot of the energy comes from. That tangles the magnetic fields. Well, the energy comes from the fusion, but then it gets tangled up in the convection, tangles up those magnetic fields because those magnetic fields come through the surface of the sun, through these sunspots, and go out into the corona. And that's where they release their energy. Let's see, here's solar wind, representation of the solar wind. Now this is really important. Here we are at Earth. Notice that Earth has a magnetic field. Now remember, charged particles can't cross the magnetic field lines. That's really good because it means that Earth's magnetic field protects us from all of this plasma that's coming off of the sun and filling the solar system and coming at us. So here you're seeing a representation of Earth's magnetic field and how it's standing off this flow of plasma from the sun. And this bubble that is created is called the magnetosphere. So a big space weather event that you might have heard of is something called a coronal mass ejection or a solar flare. Those are related phenomena, but they both have to do with big magnetic explosions on the sun and how those interact then later with the Earth. So I'm going to show you a representation of that. So magnetic field lines here, they're poking up through the sunspots on the surface of the sun. Remember, they're loaded with plasma because the plasma can't cross the magnetic field lines. And as these field lines get stressed and contorted because of all the motions at the base of those magnetic field lines, it can lead to a giant explosion called a coronal mass ejection. And the light associated with the explosion is what we call the flare. So here it goes. There's the coronal mass ejection being shot out into space. It's loaded with plasma and its magnetic field. Here's an actual video of Solar Dynamics Observatory actually imaging this type of event taking place. Back to the cartoon. And here we see this blob, this giant coronal mass ejection, this blob of plasma being shot out into space. And it'll hit whatever planets happen to be in the way. The first one, of course, is Mercury, if Mercury is in its path. It depends, of course, which way this coronal mass ejection goes and where the planets are at that particular time. The next one it might hit is Venus. And how it interacts with each planet has to do with whether or not that planet has a magnetic field to stand off that plasma, and also the characteristics of the planetary atmosphere and how that responds to the plasma and magnetic field. Now, of course, at Earth we have both. We have atmosphere that helps protect us from radiation. We also have magnetic field. So here, when it gets to the Earth, here we are at Earth, but it's okay, we've got a magnetic field. There we are. So there, our magnetic field is standing off the plasma and the magnetic field. Now, it does interact with our magnetic field, though, and in fact, the new stress that this interaction introduces into our own magnetic field causes explosions in our magnetic field. Those explosions accelerate particles and lead to the Aurora Borealis, or the northern lights. And the two experiences that I've had that are really amazing are seeing the northern lights in person. The videos, even though they're amazing, just don't do it justice. And seeing the total solar eclipse. Those are both events that I highly recommend. They're just amazing. So here's the aurora. Now this is the space weather that occurs on a big explosion day that happens on the sun. But in fact, the sun is always busy. There's no such thing as a quiet day on the sun, even when it doesn't have these big explosions. So here's back to the Solar Dynamics Observatory imagery. This is 171 angstrom, so we're looking a little less than a megakelvin plasma. So we're looking in that top layer of the sun. The sun doesn't really jerk around like that. That's just how the video is coming through. But the sun is rotating. It takes about a month for the sun to rotate, make a circle. And you can see all of these, all of the dynamics going on, all of the structure, all of the rearrangement. And remember, that's all has to do with the magnetic field. So there's smaller explosions and smaller dynamics that happen every single day. There's no such thing as a quiet day on the sun. There's always dynamics going on. And we see these dynamics on smaller scales, and we see them on larger scales. So understanding just how even these smaller scale explosions get out into the solar wind and create dynamics and interact with the planetary atmospheres and magnetic fields is something that I'm particularly studying. All right, here's another view of a different kind of dynamics that's occurring even on a quiet day. This, we're looking at a cooler temperature. This is that red that I pointed out during the solar eclipse. So this is hotter plasma in yellow and then cooler plasma in red. So there's dynamics. We're zoomed in here. So we're zoomed into the limb of the sun. And there are all these dynamics, smaller scale dynamics, but we believe this particular kind of dynamic is one way that these little explosions are helping this plasma to escape. And it escapes on one end, and then on the other end, some of it falls back to the sun at these cooler temperatures. And it's called coronal rain, which is kind of interesting. So we believe it shoots out some of the material, and then some of the material cools back down and falls down. And so we can see actually better the coronal rain because of how dense it is. And so it emits more, it's brighter. All right, now we're stepping out. This is not during the solar eclipse, but I just put this on here for scale. That's kind of the scale of the actual sun, and then this is one of these artificial eclipse movies that we see of all of the plasma and all of the variable coming off from the sun, again, during a time when there wasn't one of these big explosions. The solar wind, the sort of quiescent state of the sun as it shoots out all of this plasma, is filled with structure, filled with little explosion remnants, and filled with waves. So this is imagery taken with the Stereo spacecraft, and this is not actually the standard data set that Stereo produces. We had to do a special campaign run to see if we could pull out this level of detail in the imagery. So now I'm going to zoom in on the same set of images, but I'm going to zoom in on just a little piece of it and show this movie. And here I've got a dot here. It's hard to even see the dot. That's the Earth to scale. So you could see we're kind of, the size of the whole Earth is almost one resolution element on these images because we're so far away from the sun. So we're just resolving, these things that are just barely resolvable are still the size of the Earth and the magnetosphere. So all of this structure, when it gets to the planetary atmospheres and the planetary magnetospheres, still interacts, and the solar wind is just very treacherous. This is a simulation of what it can do when it gets to the Earth. Here I'm showing blue dots indicating where we have spacecraft. This is an actual event where we've actually recorded in situ. So the difference between remote data and in situ data, remote data are when you take pictures from a distance of the sun, for example, and you can take those images in different wavelengths and learn different information. In situ is like means right here, and so it's when you stick a thermometer or stick a measurement of the density right here, where it is right here. So here, what we're looking at is in situ data of the magnetosphere and of the solar wind. So we're looking at the solar wind right before it hits the magnetosphere. I'm going to start the video again. We're looking at the solar wind right as it hits the magnetosphere, the spacecraft right inside of the magnetosphere, and the third spacecraft that looks at the Van Allen radiation belts, and I'll explain what that is in a minute. So that's what these traces show over here. Solar wind that has these structures in it, and you can see this represents the density. The colors, I should have looped this video. Oh well. The colors represent the density, and so you can see that's the red and the yellow, it's flipping back and forth, and that's because this is meant to represent a series of those structures coming past the magnetosphere. So it rises and falls, and it's compressing the magnetosphere. It's kind of like a forced breathing. They squeeze the magnetosphere and then they relax. And then the next one comes by and squeezes it. And then it goes. And then the next one comes by and squeezes it again. And a lot of these actually come out periodically. So there'll be a train of them that repeat and repeat and repeat. And that is what makes this signature in the magnetosphere. So we see it in the solar wind. There'll be a front of structures that come through. And then we see when it hits the magnetosphere, this was the WIND spacecraft, saw that. WIND has been up there for 25 years now, making measurements upstream of the magnetosphere. Then in the magnetosphere, we see that the structures, as they hit the magnetosphere, they caused these structures, the magnetosphere, to respond with the forced breathing. Then the radiation belts, that's what I'm showing down here, respond with the same structures. So here's an image that shows the Van Allen radiation belts are these energetic particles that live in the inner part of our magnetosphere. James Van Allen discovered them. That's why they're called the Van Allen radiation belts. But remember, charged particles can't cross magnetic field lines, so they're kind of just stuck there. Sometimes they precipitate down into Earth's atmosphere, and sometimes they get energized from some of the dynamics that happen outer in the magnetosphere. So this is very important to understand, because any spacecraft flying through here is going to be impacted by these highly energetic particles. All right, so I think that was a lot of motivation on why we need to understand this and why we need to understand the sun, certainly on a big day, but also on a day when it's quiet and not much is going on. Because even on the quiet days, there's a lot going on still. So these dynamics aren't as big as the coronal mass ejections, but this is what's happening all the time. This is like the steady beat that's always happening. So what are we doing about it? First of all, we have a new mission that's coming up, PUNCH, polarimeter to unify the corona and the heliosphere. There were some stickers out there. Hopefully you saw them. So this is a mission that was just selected by NASA to fly. It's going to fly in about 3 years, hopefully. It's what we call a smaller mission, a SMEX, a small explorer. So there are different sizes of missions at NASA so that we can investigate different types of problems. So PUNCH is one of the smaller ones. It's led out of Southwest Research Institution by Craig DeForest. So the first thing, polarimeter, what is that? So let's talk about that. Light can be polarized. And this is a visualization showing how light can be polarized. Light is electromagnetic waves, and these arrows here these vectors represent the E field oscillations and the B field oscillations, the electric field oscillations and the magnetic field oscillations associated with those waves. And depending on how they line up, they can be circularly polarized or they can be linearly polarized. And how they are polarized tells you about how they were made and also about the kind of plasma or the medium that it came through before you detected it. So Punch is flying a polarizer to distinguish the different kinds of polarizations, because you can use that to understand actually the kind of structure that you're looking at. So Punch flies 4 small sats, which means smaller satellites, in LEO, which is low Earth orbit. So these are satellites that orbit the Earth and look at the sun. 4 satellites, and together we make a mosaic of polarized images. And again, it's white light, so like those artificial eclipses that NASA likes to fly. But the polarization gives us actually information about the 3D structure of the solar wind or the structures within it. So right now what we have, our current capabilities, some of those images that I showed before, fill this region of space. The black regions are blind spots. So we have a little coronagraph. Those were some of that's this square right here comes from a little piece within that little coronagraph right there. Then we have some imagers that I showed earlier. They get a little bit more of space, but they're very low resolution, both in time and in space, very low resolution. So you can see the big coronal mass ejections, but you can't see the substructure within the coronal mass ejections. And you can't see this kind of structure that I'm showing in the movie over here. So the idea with Punch is with those 4 spacecraft and combining the imagery in all 4 of them, we can fill in all of these blind spots and do it at this high temporal and spatial resolution all the time. So back to our cartoon representation. By doing that, we can understand not just the coronal mass ejection, but the substructure within the coronal mass ejection, the shock formation in front of the coronal mass ejection and any structures up there, how those big structures are interacting with some of the smaller structures that we see already are there, whether they're compressing them and amplifying them. We can see all of the structure that's there already, how they interact with each other, how they create new structures, how they combine and maybe get amplified. It takes about 4 days for the solar wind to get from the sun to the Earth. So in that time, a lot of stuff can happen. And if a very fast coronal mass ejection gets launched into that medium, the coronal mass ejection can come much faster and plow into that slower going solar wind and, like a snowplow, sort of fold it all up in front of it and amplify whatever's already there. So Punch will finally have the resolution to really image that. And the idea is to unify all of this complexity and structure in the solar corona, the solar atmosphere, with the heliosphere, with what's going on in the solar system. All right, there are lots of ways, but one other way that NASA is tackling this problem is with Parker Solar Probe. Parker Solar Probe launched last year, and the tagline is a mission to touch the sun. So this is what I was talking about, the difference between remote sensing and in situ sensing, like actually touching the plasma, literally touching the plasma with your plasma analyzer, literally touching the magnetic fields with your magnetic field measurements. So that's what Parker Solar Probe does, is it has gotten closer to the sun than any spacecraft has ever gotten before and made those in situ measurements very close to the sun. It also has an imager, but the imager is more like a microscope as opposed to a remote telescope. This is who that's named after. This is Parker. This is Eugene Parker. This mission is actually the first time a mission has been named after somebody while they were still alive. This is the first time that happened. All of the other missions that have been named after people happened after they passed away. So this is Eugene Parker. The reason it's named after him is because in 1958, he wrote a paper theorizing that the solar corona ought to expand out into the solar system, and it ought to reach supersonic speeds. And this was before we had measurements. There was some evidence, but not any sort of direct measurements of it. But he wrote a theoretical paper that said it would be true, and he was right. Here's him at the launch last year, watching Parker Solar Probe mission launch. This is the launch.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
So we had a successful launch. And what the Parker Solar Probe does to get close to the sun is it uses Venus gravity assists to redirect it so that we can get in close to the sun. And that's what this is showing here. Green is the Parker Solar Probe, and then you can see it spiraling in closer and closer and closer to the sun. So I'm going to play that video one more time. So it comes off, and then it does a Venus flyby, and that's how it uses the Venus gravity assist to steer it in closer to the sun. And each Venus gravity assist gets it a little bit closer. So we had one right after launch, and that got us in really close. And then it has another one in December, and that'll get it even closer. We've had 3 passes around the sun so far. This here is just showing its orbit, and each of these green dots is a Venus gravity assist. So it gets in close, and then it gets in close, and then it gets in close, and then we go to Venus, and then it gets even closer, even closer, even closer. That's what that is showing. So at its closest approach, which will happen 2024 and 2025, it's going to be at 10 solar radii. So if you put a ruler on the sun and had one unit be equal to the radius of the sun, then this is 10 times that distance from the sun. It's about 4 million miles. So just to give you perspective, Mercury was as close as we had ever gone before. The Helios missions, a long time ago in the 70s and 80s, had gone that close and measured the solar wind, and that was all the data we had. That was as close as we had gone, was Mercury. Mercury is 35 million miles from the sun. So we're going to get into 4 million miles. So almost a factor of 10 closer than we had ever been before. And already we're closer than Mercury, and already we're getting new data. There's way too many words to read here, so don't read them. But the point was just, this is listing all of the documents, official documents, recording the times that solar probe was attempted, or the concept was attempted. In fact, the idea that we should probably send an in situ spacecraft to the sun and have a probe predates NASA. People have been trying to do this. We knew this was the right thing to do. The problem is you have to not melt when you're close to the sun. So in fact, it required a lot of technological advances to be able to do this in a cost-effective way. The heat shield being a major piece of that. So the heat shield that keeps the heat away from all the instruments. All right, so Parker Solar Probe is investigating a number of different scientific questions. 2 of them are the things we've already talked about today. What is the solar wind? How is it accelerated to these supersonic speeds? What makes all the structure within it? And then the related question is lower down. Why was the corona so hot in the first place? what are the dynamics that are creating all of that heat? And again, we know it's the magnetic field, but exactly how is that energy being dissipated? Why does it dissipate in a chunky way as opposed to smooth? All of those different things. Why does it dissipate at the time that it does? Why does it build up a certain amount? So those are all questions that Parker Solar Probe is answering just by nature of it being closer and seeing that plasma, that magnetic field, before it has time to evolve on its 4-day adventure to the Earth. So some of the instruments that we're using to look at this, the wide field imager for Solar Probe. It's an imager. It's one of those heliospheric imagers, so it looks in white light, but it's looking off the side, and it's really more like a microscope as opposed to a telescope, because we're right there looking at the white light in the solar wind right before we fly through it. There's a magnetic field experiment that measures the magnetic field and the electric fields and some of the waves that are in the plasma as we fly through it. And then there's the solar wind electrons, alphas, and protons sweep. This set of instruments. So alpha particles, that's another name for helium that has lost its electrons. So that's what alpha particles are. But by measuring the electrons, the protons, and the alphas, again, up close to the sun, right after they were accelerated, you really can understand some of the physical processes before they've been affected by other physical processes en route on the way to Earth. So this is a simulation of some of the, this is the field of view of what that white light imager will see, because it's getting so close and it might see one of those coronal mass ejections right up close, kind of like with a microscope. Here's another. These are the existing coronagraphs that we have. And then here's, again, the Parker Solar Probe getting in close and then looking at a microscope through all of these structures as they explode and advect outwards. So I can show you today there are 3 things up here, 3 of the first light results that we had from Parker Solar Probe. Solar Probe has now had 3 passes around the sun. It's interesting, we can't talk to Parker Solar Probe very well during its encounter because it's so close to the sun, and in some cases it's behind the sun relative to us. So we actually have to wait till later in its orbit when it comes back around to actually pull the data down. So here's those images from those imagers. This is actually the Milky Way is in the field of view of those imagers. So you're seeing the Milky Way here. And then here is some of that complex structure in the solar corona as it's becoming the solar wind and sort of viewing it up close. And then this is one of the particle measurements of just that plain old solar wind plasma, but here it is flowing out at 400 kilometers per second. So that's what you're seeing here is these, the red indicates that we're seeing those plasma measurements. Now, expect to hear in the next maybe month or so some of the big announcements from what Parker Solar Probe has actually seen. Like I said, it took a while for the data to actually come back, and then for the scientists, of course, to understand what they meant, since we've never seen the plasma in this environment before.
Are the dots on that the sun?
No. So this is the Milky Way. The dots here are other stars. I believe there are planets in here, but I can't be positive which ones. And I believe that that's a planet, but I don't remember which one. Yeah, the sun. So in both of these images, the sun is way, yeah. And so these are imagers that look off to the side. So Parker Solar Probe, as I said, had 3 orbits. It's about to do another Venus flyby, and so then we'll get new kind of data as it gets in the next step closer to the sun. So that'll be really cool. And we're really excited by that. So the takeaway that hopefully I've convinced you of is there are no quiet days on the sun. Even during its most quiescent time, the solar atmosphere is still filled with waves, explosions, little explosions, big explosions, energy bursts, structures. This launches dynamic plasma out into our whole solar system. And this dynamic solar wind is constantly bombarding all of the planets, including us, including the Earth. So that's really important for us here at Earth, but it's important for the other planetary systems as well. And it creates this dynamic space environment that we live in, even on a normal day. Thank you.
Thank you, Nikki. And now we can take questions, and she will repeat them so everyone can hear. Please ask your questions.
Yes.
You used the word chunky, which I really like.
Yes.
And I'm just wondering, in a sort of big picture way, should we expect that the sun is more uniform and that the chunkiness is sort of an exception, or should we expect that it's more chaotic and that the uniformity is kind of the unexpected?
The unexpected relative to other stars, or relative to the sun's lifetime, or relative?
The physics of how stars work.
Yeah. Yeah, that's a whole, we could have a whole discussion about that. Magnetic explosions, we also call those magnetic reconnection, seems to be inherently chunky. It seems to be, it doesn't just happen in a laminar fashion, it sort of goes in bursts. So it's kind of wherever you look in the universe where magnetic reconnection is occurring, that does sort of seem to be bursty or chunky, or pieces sort of restructure. So that seems to be a universal thing. Waves, which will interact with different kinds of plasma differently, like it might find a resonance over here, and so it'll only focus its energy right here, but it won't find a resonance over here, and so it kind of just passes through. So that'll be something that will tend to create structure. So I think, yeah, structure and chunkiness, burstiness is probably a universal feature. The other thing is, what's controlling these dynamics is the magnetic field. The magnetic field on the sun, certainly, and we know that this is true on other stars too, goes through a solar cycle. So the magnetic field builds up. It has more of those active regions, those regions of intense X-ray and ultraviolet radiation that are associated with the sunspots. Gets more intense for 11 years, and then we reach maximum. And then it goes away, and then the polarity flips on the sun, and the whole cycle starts over, but with the reverse polarity. So that's the really long scale, but that magnetic field and how intense it is and how it's trying to restructure itself is going to be part of the story. And so stars with different kinds of magnetic fields or more active magnetic fields will maybe have more or less of that. Yes?
Yeah, so when I was looking at the pictures of the sun and I was rotating, it looked like there were two bands of like major activity. I was wondering if that was just if that was actually happening or just a pattern. But.
So the bands on the sun in, I'm going to see if I can pull this back up.
Yeah, it was kind of far back.
So when we were looking at the video in 171 angstroms, which is sensitive to a little less than a megakelvin plasma, and there were different bands. So we're seeing, I think, let's see if I can get back there. Eventually. Here it is. Next one. Poof. Here we go. All right. These bands. So there are definitely bands of activity on here. There's active regions, which are these intense regions of ultraviolet light that are associated with the magnetic field concentrations and the sunspots. There are also these dark bands. Those are filaments. They look dark on disk here in this particular wavelength, but off the limb in that cooler wavelength, you would see those filaments glow in red. They have cool material. Those are locations where a lot of magnetic field stress has built up. Sometimes those erupt actually and are one way that we can get coronal mass ejections. So yeah, there's definitely bands of activity that persist for several solar rotations, both in terms of the filaments and also the active region locations.
And is there more going on around the equator versus the poles? Is that just what we're seeing?
Both. There is an equator because the sun rotates, so that does sort of set amid like poles in a mid, and the magnetic field does organize itself around that because of the solar dynamo. So there is an equator, and the active regions, those active polarity spots, do pop up on either side of that with certain polarities depending on where it is relative to the equator. And your question about the pole, does the pole have more or less activity, or can we just not see it? And the answer is yes to both of those. It is hard to tell for sure what is going on over the poles because we're here at the equator looking far away. So going over the poles would be really cool to do. There was a mission called Ulysses that flew over the poles, but it only had in situ instrumentation. So it has evidence about what the poles look like, but it didn't have an imager to look. So that would be a cool thing. So yes, there are definitely times where it looks like the poles have a different kind of activity than what's going on. The active regions, you don't see active regions, for example, up at the top of the poles. They sort of, they pop up sort of here at these mid-latitudes, and then as they advect, actually, they get convected up to the poles, and then they kind of dissipate. We believe that actually has to do with how the next solar cycle is set up. Yes?
What was the heat tolerance that Parker was built to
I
survive?
I don't remember off the top of my head, but yes, they definitely did a lot of testing of the heat shield to make sure, the requirements are always that we withstand X number more than what we actually expect the environment to be.
How many rotations will it actually experience before it hits the limit?
Yeah, so 2024 might be our last orbit around the sun. And what happens is we run out of propulsion to hold the heat shield in front of us and the sun. And so that's when things don't go well anymore. But that's part of the plan. I mean, that's, you can't carry infinite propellants. So we have, I think it showed it maybe in one of those movies. We have mini orbits. We've already had 3. About every 6 months right now is the cadence, but then they go faster later. Yeah, so we could count these up. That's how many orbits. Each one of these blue guys is an orbit around the sun. So we have the orbits, of course, go faster as after we do the Venus flybys, and we get closer. So we start to go faster around the sun, and then we have more of them. So we have many, many orbits. Now, we don't take data when we're far away from the sun. We only take data when we're close to the sun, mostly. And that has to do with the ability to talk to the spacecraft and bring those data down. Yes?
The illustrations seem to depict the magnetosphere as like a donut shape around the Earth.
The Van Allen belts?
I guess so.
Yeah.
And so are the poles of the Earth much less protected?
Oh, I'm not repeating.
You heard me.
The poles,
I know. Start over.
sorry, say again your
Sorry,
question,
are the
please.
poles less protected by the magnetosphere?
Ah, yes. Okay. So are the poles less protected by the magnetosphere? In some ways, yes. So these field lines here over the equator shield us from the plasma from the solar wind and from these coronal mass ejections. These field lines here are directly open to the solar wind and connect to the magnetic field of the rest of the heliosphere. And so, yes, there can be some direct access of energetic particles over there. In fact, when we have a big storm, flights will be rerouted so that they don't fly over the poles because of that direct access of the energetic particles over the poles. Yes?
So it sounds like some of the observations about our sun helps us better understand other stars out there.
Mhm.
Is the reverse true? Like, does that distance sometimes help us understand our own star better? Maybe about what's going on at the poles, since we haven't been able to observe that very well?
Yeah. Yes. So in general, more data points, more than one data point about other systems is always a good thing. We get different kinds of information from the stellar observations, but indeed there are a lot of sun-like stars, and even thinking about like how the habitability of those solar systems around those stars is also a piece of that story. Yes, we get different kinds of information from the other stars, and that helps us piece together what our star maybe looked like before, what it might look like in the future, how some of these universal processes like the magnetic field intensity and how those magnetic fields make different kinds of dynamics. We can definitely learn information from looking at other stars. Other questions? Yes?
So I saw a couple of days ago there was some reporting about Voyager 2 hitting the border of the solar wind with the extrasolar system.
Yep.
Radiation coming in. Did that yield something of interest here in terms of the solar wind, and what it does at the limits of the solar system?
It is generally related, but not specifically related to what we're looking at here. The heliopause is where the Voyagers crossed. So just like there's the magnetic field of the Earth carves out a boundary around Earth because of the plasma not crossing the magnetic field lines, and we call this the magnetopause. There's an equivalent on a much larger scale, the solar system. So now imagine this wasn't the Earth in here, but imagine the sun in here and the sun's magnetic field, and that this is the interstellar plasma. There's sort of an equivalent bubble formed by the plasma from the sun and the solar wind and the magnetic field from the sun, making a plasma bubble, the heliosphere and the heliopause. It's at about 100 AU, so 1 AU is the distance between the Earth and the sun, so 100 times that. So by then the solar wind is very diffuse. It's had a lot of processing. So in terms of helping us understand its formation, it doesn't do so much of that. But in terms of understanding these fundamental plasma processes and how magnetic fields interact with the plasma, it's definitely an analogous sort of situation. The interstellar medium might be impacting our heliosphere in a similar sort of way. Yes?
How does this temperature differential work? If thermodynamics was working, it would try to reach an equilibrium temperature between the surface and the corona.
Mm-hmm.
There doesn't seem to be a temperature gradient in there, just like it's 6,000 here and 6 inches away it's 6 million or whatever.
There's actually a very steep temperature gradient. It's called the transition region, and it's this location where it's more than 6 inches, but it is pretty steep, where it goes from 6,000 is the temperature of the photosphere. There is a layer above that called the chromosphere, and the chromosphere is tens of thousand, 10, 20, 30,000 Kelvin, so it's a little bit hotter. But then between the chromosphere and the corona, there is a thin transition region where all of a sudden the plasma goes from 100 Kelvin to 200 Kelvin, 200,000 Kelvin, up to 1 million very rapidly. But we can see that there is plasma on the way, that there is plasma at 100,000 Kelvin, and there is a little bit of plasma at 200,000 all the way up. So we can measure that transition.
Do they ever reach equilibrium?
They are in an equilibrium. So you can work out the hydrostatic equilibrium equations actually for the solar corona, and because of this magnetic connection back to the chromosphere, the plasma in the corona will emit some of that energy out as radiation, and then it actually thermally conducts some of that energy back down into the chromosphere, which is very, very dense, and so it will radiate some of that energy away through light too.
Just a quick question. So what is the Parker probe's fate once it's just going to burn up and...
Yeah.
That's
What is Parker Solar Probe's fate? It might just burn up. Yeah, it's
once the heat shields are down.
by design. It of course we keep taking data as long as we can, but by design it has a certain amount of propulsion to hold that heat shield, and then when it runs out, then that's it.
Just burns up.
Yeah, and we should have another one, and then we could see more.
Where is the solar observatory located? Is it terrestrial?
Which solar? I showed many solar dynamics observatory. The Solar Dynamics Observatory was one of the spacecraft that I showed. That one is also in a LEO orbit, I believe. So it orbits the Earth and looks at the sun. The stereo spacecraft, it's called stereo because actually there are two of them, so that they can look at stereoscopic views and get 3D information about the coronal mass ejections. I didn't highlight that aspect, but stereo is in very similar orbits to the Earth, but one slightly ahead of the Earth and one slightly behind of the Earth. And then they slowly go around relative to us. And then we have spacecraft, other observatories that sit just upstream of the magnetosphere so that we can see stuff. Is sort of think of it like those tsunami buoys, like you see the stuff right before it hits. So you get a warning in that sense. And then we have a whole bunch of spacecraft that sit and orbit the Earth in the magnetosphere. Yes?
Is there any relationship between the degradation that's occurring with the atmosphere and its possible effect on the magnetic field? Or are they completely separate and distinct?
Yeah, the magnetic field of the Earth is set deep down in, the Earth has its own dynamo that creates the magnetic field. So that's definitely an independent process from atmospheric things going on the Earth. Yeah.
Thank you all for coming.
Yeah,
Oh,
just
you
one
can
quick
come up and
question
ask.
about Parker.
Sure.
Why couldn't it just go around the sun at a close distance? Why does it have to keep going around Venus? And it seems you get a lot more data.
So we start off going at the Earth's velocity when we launch a spacecraft. The spacecraft is traveling with the Earth, so it's going with the Earth's velocity, which means actually it starts off at the orbit of the Earth, because how fast you go is how far away you orbit. So you actually have to go the opposite direction. You have to get a delta velocity, a change in velocity. You have to get rid of velocity. So we use Venus to get rid of the velocity. Actually, some of the original ideas were to go out to Jupiter and use the gravity of Jupiter to get in even closer, but there were some pros and cons of that approach. So the Venus approach is the one they went with. But you got to get rid of a lot of velocity to spiral into the sun is the key point.
Thank you all
Thank
for
you.
coming, and thank you.